This is a paper done with, started while I was at Stony Brook and then finished up with some collaborators from Yahoo Research, particularly Yufan Hu. In this paper, so we're working on graph representation. And if you're not familiar with this problem, what you're trying to do here is come up with a small embedding vector to represent each node in the graph so that you can use that feature as a feature for like later on machine learning tools. So instead of the adjacency matrix, we're thinking in some kind of latent space that's a lot smaller than the adjacency matrix. There's a lot of recently popular methods that do this. I'm going to call them all DeepWalk derived, so DeepWalk, line, node-to-vec, et cetera, et cetera. And all of these things are just trying to somehow compress the graph in a latent space. Visually, if you think about this, instead of this discrete thing with the edges, you get something that's two-dimensional in this continuous space where you hope that the community structures are kind of preserved. The colors here are community structures, and they correspond to like a max modularity partitioning of the input. And so what are we trying to do? A lot of these models use skipgram, which is a really flexible model. It does a good job of learning representations. But the problem with skipgram is that you're not sure that you found the right representation. It can get stuck at local minima, and as the graph gets larger and larger, you can imagine that you find more and more local minima. So the existing methods that I've mentioned, DeepWalk, line, node-to-vec, et cetera, only explore the local neighborhood around the nodes. This is kind of great because it makes them more scalable, but they run into this sort of corner case where they can fail to preserve the global structural information that's in the graph. A visual example, actually let's talk about our solutions. I didn't make these slides, so this is going to be a little rough. Our solution to this problem is to do multi-level graph representation learning. What we want to do is build a series of smaller graphs that preserve the structural properties that are present in the input. So looking at this kind of like road network, as you start collapsing these nodes together, and you get something that looks kind of more and more coarser, with many, many less nodes and edges, but has the same general shape. And so the idea is that if we can do this coarsening, then we can kind of do the embedding in reverse, embed the simple shape and use that as an initialization for the subsequently more complicated shapes, such that the embedding we get at the end preserves the global structure of the input, in addition to the local structure. And so this approach is sort of compatible with any graph embedding algorithm, because really it's sort of our idea is sort of this hierarchy of coarsenings, and then sort of this going through the hierarchy of embeddings. And why is this useful? Well, embedding a smaller graph is usually easier, and so I'm sure that you guys can come up with counterexamples. But there's a possibly smoother objection function. Basically, you have less pieces that you need to put in the right place. The graphs have smaller diameter so that their global dependencies can be modeled by local algorithms. And those two things together actually do a pretty good job of delivering global structure. And so I can show you some pictures, all right? Because this is maybe why you'll believe me. So if we start with something that is like clearly a ring, we can express it that way. Some embedding algorithms will learn like something that doesn't look very much like a ring, right? And so these still could perform well on some tasks, but you really, in my opinion, want to see this big hole in the middle where nothing's similar to nothing else. And so if you take the same algorithm and you run it through our pre-processing, you can get something that looks a lot more like a ring. Similarly, here's another 2D structure. Here's a grid. You get something that doesn't look a lot like a grid here or a plane. But if you do this again using our preprocessing, you get something that looks like a plane at the end. So really, it's sort of this paradigm is about just kind of preserving these global structural properties that previously might be ignored. So the paradigm is really straightforward. We have kind of two heuristics for graph coarsening, and they're inspired by the graph drawing community. So these are actually used for like two-dimensional graph layout algorithms. And so if you've used something like Gephi and like the Yufan Hu layout, this is exactly what it's doing under the hood. So we're trying to find a set of like independent vertices. So we collapse some edges. This is one way of kind of getting rid of at least half of the vertices, or keeping at least half of the vertices. But if you have these real-world graphs, you need another trick. So we have a sort of a hybrid approach that uses this edge collapsing and this star collapsing, because edge collapsing doesn't work so well when you have star nodes. And so the star collapsing is instead collapsing around the high-degree nodes, their neighbors directly. And so this hybrid approach, where all the nodes with degree higher than k, we do the star collapsing, then we do edge collapsing iteratively on it. That's kind of like the coarsening step that we use. I can talk more about this later, but I'm going to just keep going for the sake of time. Okay, so now we have the graph. So we have a bunch of coarsened graphs. So the trick is how do we embed it? And so what we actually do here is normally when you learn these graph representations, you initialize the parameters randomly. And what we do instead of that is just initialize them with their the previous graph's embedding of their parent nodes. So we embed the hierarchy using whatever graph embedding algorithm you have. We take those parameters and we use them to initialize all the children. So all the nodes that were coarsened now get the parents' embeddings is what they start with. And so you can say that the initialization there is not random. We hope we find one that's better than a random initialization. What does this look like, just to kind of bring it in? So for this plane graph, we kind of embed this down to a series of like 2 or 3 triangles, and then you can see we kind of grow it. We grow out from there. So, and this is what each of the steps of the embedding looks like. So we were able to embed, level 7 pretty well, and then we get kind of coarser and coarser and coarser until we get to as many nodes as the original graph had. So we did some experiments with these 3 named embedding methods, and we try to control for the number of samples that each embedding algorithm has, and make sure they all use the same learning rate to kind of measure the effect of the approach. In general, what we see is sort of like a bump, and the bump is bigger sort of the more local the algorithm is. So line is the most local, so you see like a big bump. Node to vec has like some parameters that can kind of make it really far reaching, and so the right parameterization of node to vec, you see like less of a jump because it's already looking at more global structure. DeepWalk falls somewhere in the middle of those two. But the red line is ours, so you can see kind of improvement on these classification tasks. The nice thing about the preprocessing, although it is a heuristic, is that it's a linear overhead, so it's linear on the size of the graph. So it adds kind of like not much additional asymptotic complexity, no additional asymptotic complexity, and not much additional running time. And embedding small graphs is also pretty cheap. So you spend only half as much, twice as much time as you might normally spend. So in a log-log plot, you don't even really see it. So that's the paper. I have no idea how I'm doing on time, but I'm assuming I'm okay. And this is that's the big idea. I'd be happy to talk about it more. And we should have code coming shortly once my co-author sticks it on GitHub. Thanks, guys.